though I think most of the uh, people over here, participants, know you, but still. No, Dr. Nikunj, is the slide visible?
Yes, madam.
Okay,
It is
know
visible.
you,
Yes.
but so today's session is by Professor Amit Seth. He's the founding director of the Artificial Intelligence Institute, University of South Carolina, USA. And the topic of his talk today is robust and trustworthy AI for mission critical and enterprise AI applications, neurosymbolic, custom, compact, and agile AI models and co-pilots. So Professor Amit Seth is an educator, researcher, and entrepreneur. He's the NCR Chair and Professor of Computer Science and Engineering. As a founding director of the university-wide AI Institute at the University of South Carolina, he guided its growth to nearly 50 researchers in its first 4 years. He is a fellow of IEEE, AAAI, AAAS, ACM, and AIA. His awards include IEEE CSW Wallace McDowell and IEEE TVS VC Research Innovation Awards. He is one of the highly cited computer scientists worldwide with an H index of 120, more than 61,000 citations, and an I100 index of greater than 144. He has co-founded 4 companies, including the first semantic search company in 1999 that pioneered technology similar to what is found today in Google Semantic Search and Knowledge Graph, EZDI, which developed knowledge-infused clinical NLP and Cognovi Labs at the intersection of emotion and AI. He is particularly proud of the success of his more than 45 PhD advisees and postdocs in academia, industry research, and entrepreneurship. So, we welcome you to this session, and we are very thankful that you could join us today. So, over to you, sir.
Thank you very much. It was wonderful to connect to you. I'm glad to see this number of people who have signed up. May I briefly know who is the audience? Are these LNMIIT students, and are they all in computer science, or what is who am I talking to?
Okay, so they are faculty members from Technical Institute Span India.
Oh,
Apart
okay.
from, yes, most of them would be having a background of computer science, but there are some with electronics or mechanical background as well. Then we have research scholars. We also have officers from DRDO organization, the defense organization DRDO. So it's like a diverse audience, and I think they are probably all having some basics of deep learning.
Okay. For my for the DRDO friends, I actually have a white paper on sovereign AI for strategic autonomy. The idea came to me after my meeting with the Prime Minister and my keynote at the third annual Chief Secretaries meeting on, I think it's just, yeah, on 27th of December last year. Um,
Okay.
uh, and so, India has a lot of opportunity and challenge in making sure that the mm, AI is completely owned by, like any other technology, but AI is certainly owned by the country and secure and other issues. Of course, today I'm not talking about those issues, but feel free to reach out to me for my concept paper. Today's talk is, let's see if I can. Um, I see. Uh, Give me 1 second. I'll have to transfer the talk to another. Uh, yeah. Okay, that should do. Okay. All right. Now go to share. Okay. Can you see this? Ah, now it is showing up.
Yes, now it's visible.
Okay. Now is oh, just finish the window. Huh. Okay. So we're going to talk about a robust, intelligent, and trustworthy AI. People would expect that AI is intelligent, but actually, not exactly. Not all the AI, not current AI, or there are different facets of um AI that could be more intelligent. And let me start with a little bit of introduction of what my team does, what we do at AI Institute. We work on a whole area of a whole number of areas of AI. You can see them in the uh, inner ellipse. And today I'm going to largely talk about the topics in the red. I'll say a little bit about generative AI also, since there is time. I believe you've given me up to 90 minutes. Am I right?
Yes, Professor Seth. Yes.
Yeah. Okay. So I'll little touch upon very little bit about generative AI, because this is so important. This is something that people talk about the most, and I want to make connection between the most popular and state of the art AI with the next generation of AI that we are working on. The kind of topics that at least I feel will become very important. In the process, you see on the outer ellipse a whole lot of applications, and I have well, I think I did not put defense intelligence, but I have. I'll today talk about just a few of them by way of examples. But you can see that one important thing to note here is that AI has such a wide application. It's a very core and basic technology, just like software is a very basic technology. So AI, people are talking about AI operating system, and it's going to be, is use is currently widespread in certain type of work, and will be widespread in the future, in 5, 4, 5, 6 years. Uh, this is my this is the AI Institute. You can see on the top left, this is the group of people who moved with me from Wright State University to when we moved to Georgia, sorry, to South Carolina. And in fact, that even includes one alumnus who was visiting me from Samsung Research. And then over the period of time, we have grown substantially. On the bottom right was the first PhD student who graduated from here. He's a faculty at UMBC. Um, okay. Uh, the the talk will be today about overview of the challenges in generative AI, and motivation for robust and trustworthy AI. And then I'll briefly deal with some of the challenges in generative AI, and then we will go on to robust and trustworthy AI. And within that, we are trying to look at all of you probably are aware of the AI models like the GPT behind Chat GPT or Llama 3. So those are the large language models. I believe that we we are moving towards a different alternative, and very soon you'll see many more different models as we go along. um, So let's look at what's happening today in generative AI and where we are. So US's defense agency DARPA, which funds a good bit of research. In fact, the internet came out because of DARPA. Um, has talked about, and most people recognize AI in three phases. On the left hand side, you see AI called symbolic AI. You used to have rules and logic and expert systems. Then came machine learning and other forms of statistical machine learning. So you had traditional machine learning, you had deep learning, and the deep learning had quite a few successes. So we have seen, for example, radiology. The ability of today's radiology screening system is on the average better than a human expert radiologist. So interpretation may not be as good, but classification is extremely high quality. And there are many other success stories, protein folding, and in chemistry and drug development. So that is fantastic. And then there is this latest is the evolution of large language models. So the idea has been to collect very huge amount of data from anywhere you can find it, and then a let a technique like transform let loose, and then you get from it the highly huge parametric space, which is exceptionally good at some of the things it does. Now, it comes with a lot of challenges and problems, so we'll discuss a little bit of those challenges and problems, and then we'll move on to um, the kind of application for which LLMs are not the best solutions, and that we need different kinds of model and different types of not just the model but the AI systems themselves, because humans don't just interact with AI model; they interact with the system. Human typically, most of you would not be using GPT. You'll be using Chat GPT, and Chat GPT is a collection of systems, collection of things, and you call that AI system. And how do you make them appropriate for certain kind of complex, mission critical, and enterprise applications? That is what we're going to talk about today. So at a very some of you who know the current generative AI know that the current language models essentially are predicting the next word, and what is the most likely next word. And essentially, to find that, they look into this parametric space you see on the right hand side, and they essentially predict which word would be the next. This is a very high dimensional space, bit hard to visualize for us. This is also called distributional semantics, and uh, in the with the words that are preceding can give the model the context it needs. Now, this technology has become exceptionally good at a certain kind of task. I'm going to characterize them as information assistant task. So you're doing question answering, you are doing coding, you are doing editing, you are doing content generation. You are helping you using it to generate your email, even to respond to an email. So the interesting thing is that it is possible that your email is read automatically and your answer is given automatically. So the machine can talk to each other. Humans can stay out of the way, or at least just be a supervisor. And so that's a strange new world that we are going towards. And this technology has impressed so many of us. Uh, so for the thing that it does, for the things that it does well, it's amazing and it's exceptional. But it has a lot of problems. I'm going to talk about it, and so we have to be careful. And the second thing is that there are class of applications. I would call them decision support assistant applications that require planning, causality, cognition, reasoning. These things are not served well by generative AI. Generative AI, large language model as we know today, are not capable of serving them. They just don't it's just a different purpose, and that there are a lot of problems if you were to try to use language models for such applications. In the context, the there was a paper that you can see in the blue, consent in crisis, rapid decline of AI data commons. One problem that was identified is that the models on which this is trained on is uses vast amount of data that is collected on the web. But the problem is that there is a lot of AI generated data now. There's a lot of data, there's a lot of junk that is the amount of AI generated data, which I'll talk about briefly later on, is growing, and so that is contaminating this content, and that can lead to poor quality of results. Now, there's another important very consideration. You see that picture. Darren Esimogu is the one of the three Nobel Prize winner in economics this year. Now he was talking about whether the current AI is relevant to high and useful for high value business or industry use cases that impact productivity. And he presented statistics that AI can do only 5% of the jobs. Um, that means there is a lot of scope. Not that 100% of jobs needs to be done by AI, but there's a lot of scope for developing AI that can do more of the task. Um, Heroes, in just about a month ago, Gartner came out with statistics that today just about 1% of the AI models, generative AI models, are used by enterprises. And there's some other statistics that talks about some other number, but it's very low. And um, within 3 years, there'll be other models that will come up to support high value applications. An example could be clinician decision support. You could not be making mistakes, otherwise you'll have a human, and create personalized treatment plan. Where you have to provide a lot of contextual information about a human. And another statistics that a lot of Gen AI project will be abandoned due to data issue, risk, cost, and unclear value. So, for example, in healthcare projects, poor decision support coverage due to lack of domain expertise, adverse outcome due to internet inherent model properties like hallucination, contamination, and high cost of AI model deployment in clinical settings. Also, privacy, because for example, if you're using ChatGPT, all of that data, all of your conversations go to OpenAI. So here are some of the issues that uh, have been noticed. ChatGPT showed only 50% accuracy in medical queries, raising concern about trustworthiness in clinical issue. There is, when you are applying, let's say, in clinical application, doctors have to follow clinical guidelines, and LLMs rely on outdated and incomplete information, and you may have medical or clinical guideline that doctors have to follow that may not be the language model does not have the specific guideline that an asthma specialist or a cardiovascular international cardiologist would use. Now, if you are in a medical practice, you have to follow those guidelines. You do not have the option, otherwise you will hurt human as well as risk litigation. Domain specific expertise is very important. and there can be bias and other harmful outcomes. What has been happening is that uh, AI use, particular generative AI use, is been creating a bunch of problems. Look at the headlines on the left hand side. The rise of AI fake news, right? And these bots, of course, are also examples of AI. Um, and that hallucination, images are made up, um, and people can easily, suppose there is a crisis in Manipur, people can easily make up images and present as that to be the case. The interesting thing is that as the AI creates harmful impact or creates problem, you also need to develop stronger AI to counter that. So there is a cat and mouse problem. And on the right hand side, for example, we had a paper talking about building trustworthy neurosymbolic AI system for consistency, reliability, explainability, and safety. So I'm going to talk about some of these today. And there are many other challenges that we'll discuss as we go along. Another issue is that what is generative AI currently being used for, where it is very successful. So the paper that I mentioned here, Consent in Crisis, that analyzed 1 million ChatGPT queries. And you can see that the kind of application it has been used for on the top left. um, Top use case is creative composition. So if you're a content editor, this is great. Second most popular is sexual role playing. Third, other common use cases are brainstorming, planning. For example, you could say, I am visiting this national park, help me create a 2-day or 3-day plan for me. And it can do very good job. You may then customize some explanations, it does well. But these, as you can see, these are not really decision making queries. They are not the queries that can lead to a lot of actions in targeted cases. Yeah, action in the context of visiting a national park, yes, but not in many other cases, not in, let's say, factory on a factory floor. So for the high quality um, business use cases, industry use cases, there is a lot to go. Now, what are the risks associated with this? The risks are lack of transparency. AI models can be unpredictable. Accuracy issue. I can, you can never promise that the AI system will not make up the information. That is the nature of the AI system. Basically, the generative AI is exceptionally good for memorization and for the task that can be solved with memorization and pattern matching. Bias detection, is a problem. Intellectual property risk, because these AI systems would take the data that you give. Cybersecurity threats and sustainability concern. Of course, Microsoft just paid for three-island nuclear plant that will cost $1.5 billion to just restart, and then $1 billion a year. So there are many use cases. Google's AI chatbot Gemini tells users to please die, or you are a waste of time and resources. That kind of stuff happens, and many other issues that may come up in terms of asking to use glue for pizza. So what is the solution? Where do you get the solution? To start off, that is are these three very important terms: instructability, grounding, and alignment. And there are a lot more. Instructability is about the fact that AI system that may be, and I'm putting it very simplistically because there's only so much time I have. But AI system like generative AI system is trained on massive amount of data, but it may have been last trained in 2023. It does not have latest information. That information can be given from outside, and there are also more feedbacks and you know additional learnings that humans can do. RLHF is very well known, but there are other emerging techniques that would provide AI systems. So don't think AI system as knowing it all, and let the humans or other technological way, let us provide additional information in technological way. Grounding is another thing where you make AI system aligned with the or connected with or supplied with the real world concepts, um, and then alignment itself, that you make AI system behave in a more value centric manner, uh, in a way that is consistent with human values, with laws, with regulations, policies, guidelines, and such. Um, so we've been working on neurosymbolic AI as a way to do that, and there are a whole bunch of things to take care of: consistency, reliability, explainability, safety, trust, to make applications, important applications, uh, you know give you what you want. Just another example is here is that uh, you ask um, a generative AI system to explain the answer, and the problem would be that it'll give you an answer that is not very specific in the context of user knowledge, human knowledge. Let's say that a clinician asks questions that relates to uh, depression, and if you if 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 you want explanation as to why the AI system comes up with what it does, it needs to incorporate domain knowledge such as PSQ9. These are the nine different question considerations that um, um, goes through. For example, patient's appetite, or patient's energy, or sleep problems, or suicidal thoughts. So you have to formulate your answer that incorporates those specific domain considerations. Okay, let's quickly look at challenges with generative AI, and we are going to talk about a subset of these. So today, we'll talk about hallucination, AI generated content, misinformation, and one more. Um, First problem is it AI or human? So what has happened is that today the generative AI is so good at natural language generation, or for that matter, image generation, that at times it would be very hard to say whether it was generated by human or machine. And if you think about regulations, so suppose a regulation says that you need to identify um, content that is human generated or machine, where it is machine generated. Well, that would be very hard to do. Many times, when students use Chat GPT and answer a question, it may be impossible for a teacher or instructor to say whether it is Chat GPT generated or machine generated or written by human, right? Um, we had a paper in EMNLP, that is one of the top two conferences in NLP area. And this paper, you can see at the bottom, won the Outstanding Paper Award. Um, and here we looked at various factors, uh, bustiness and perplexity, stylometry and other things, and we compared 15 large language models. And as the models become more as we develop larger models, it has become more human like in content generation, and hence harder to detect if the content is AI generated or human generated. So this is a very important problem. Um, in the context of AI, it is possible to generate the images, some of the images. You can see the image of Pope, and that by doing visual paraphrasing, it's a kind of attack you can do on the images. You can change the images, morph it, and to look different, but it would be impossible to say whether it was human generated or machine generated. So that is a very challenging problem that you have to solve. And 90% of all online content could be synthetically generated just by in less than 2 years. So there are techniques that we have been developing. One of them is called visual paraphrase, Pikavi visual paraphrase, a text safe and distortion free image watermarking technique. And this is a work in progress, but there are variety of paraphrases on the image you can see in the picture, and that in the image you find a particular part of the image that changes the list with the paraphrase uh, attack. And then what you do is to then that region which is stronger region, you put the watermark, and this is a way image with salient region that you watermark, and makes it and then you encrypt the parts, and put it into the header file, so only people with the right permission can look at it and decide whether the image is uh, machine generated or not. So uh, the next major issue is information misinformation, deepfakes. So here EU has a code of conduct against hate speech, but evaluation is very hard. You can see the image that I created for just by giving the prompt about Elon Musk marrying Kamala Harris. This was done before Elon Musk became very busy with supporting Donald Trump. Um, and the text, same about the text. So we did that. It's very easy to use AI models to create misinformation. And 2 years earlier, a survey said that 10% of the social media user use AI to uh, create fake misinformation or fake news, and 56% knowingly forwarded this. That's a huge problem that we face. Now, and so we have some papers in this area, and we also run a series of workshops where we create a very large corpus, and have shared tasks and invite people to participate in the competition. Here is a very interesting example, with regards to multimodal fact verification. There's this post you can see on the left hand side where it says, "I got to work with Magic Johnson last month when he came in the hospital, in our hospital to donate blood." And you can see there is even a photo, right? Well, it's actually fake. And one of the things that we have done is to build this 5WQA based explainability. So we ask who claims what is the claim, when was the claim made, where was the claim made, and why the claim. And then it automatically gets the answer for many of these things. It's not a perfect tool, but compared to the fact checkers, let's say news organization, this does far more activities. The way I would say is that this could be used by fact checker to substantially improve their productivity. Now, how would you solve this problem? And here, this is a very important point, that I would like to explain you. The way to solve this problem is to identify the fact that Magic Johnson is HIV positive, and HIV positive people cannot donate blood. So with that, then uh, that is the knowledge, and you have to find this applicable contextual knowledge and apply that. So even the most important point I want you to take away here is that there's no way a generative AI system can solve the problem with its world class statistical processing, right? I mean, it creates this exceptionally good information from the data. It learns from the data, from the training data, but it will be missing this knowledge. And so we have to bring in this knowledge. That's why you can see here knowledge infused visual language modeling. So this is the kind of work that we've done, and NSF has funded a project just to work on this kind of problem. And so we are developing Neurosymbolic AI solution. Next is a hallucination, and I the kind of that this became the 2003 word of the year. um, by the way, uh, it'll be, I hope some of you know what is the 2024 um, word of the year. It is brain rot. That's very interesting. Well, let me not diverge here. But when AI hallucinates, it produces false information, and that such a thing could, though, be easily done by a system. And now, this kind of hallucination can happen even in the visual content. So, for example, you're seeing some of these here clips, and say temporal dysmorphia is the kind of things that AI system generates, but could not have occurred when you look at the order by time, or in the subject multiplication reduction, you may see that let's say a human just disappear from the image, right? Something like that doesn't happen. So these are the and this was just generated last month, or very recently. um, with ChatGPT, um, uh, there is a lawyer that used ChatGPT, and he was found to have used ChatGPT, and he could, the interesting thing is that in one of these cases, ChatGPT created even the past cases. So in a legal brief, you have to say you're building an argument based on the past rulings, and the ChatGPT simply made up the rulings that were never there in the real world, right? So this is a huge problem. The lawyer was found and countersued. Uh, so characterizing this hallucination is a major problem, and we developed a classification for that. You see on the left hand side, and then we created this hallucination vulnerability index, and as you can see, there is a higher hallucination as the models have become more complex, right, from bottom to top. So larger LLMs without RLHF are prone to both orientations of hallucination and in other things. So, and there are many other details that right now I'm not going to talk about. But this paper also was nominated for Best Paper Award, and there was a very big article in a piece in Washington Post discussing this work, and our student was interviewed for that. Okay, so by now I've shown you a whole variety of problems that occur, the whole variety of challenges with the generative AI. This is very um, uh, so we are at a stage where AI is doing some wonderful work. At certain problems, it solves very well, but um, there are what I will do is now to go towards a class of problems that we can still not um, uh, solve very well. And what do we do? So again, um, how the AI is moving. We believe that now we are entering the third phase of AI, and we believe that is through this neurosymbolic AI. So the point here is that your symbolic AI of the last century, you have statistical AI for this century so far, more or less, and that we are entering this next phase where you might say, well, okay, we for 20-25 years we really made huge progress in the second wave of the AI, and the third wave is what we are entering. And why? And going to try to explain, what are the unique things about this next phase, what we are doing uh, as our contribution to that next phase. So here are some of the challenges that we address. Um, I'm going to pass that. Um, so now we are talking about this word neurosymbolic AI. So we basically have the symbolic part. You see here in this image, symbolic part is on the right. One form of representation of symbolic information is knowledge graphs. This knowledge graph word recently DARPA published, sorry, not Gartner published a piece where it touts a huge value of huge importance of knowledge graph as we go forward. And in the left hand side is your statistical AI, natural implicit parametric knowledge representation. And now the idea is to combine the two, and you combine this um, that in a way that may also involve human expert, for example through instructability, right? So what you do here is um, and this kind of technology is going to be much more valuable for the class of application that generative AI cannot solve well, which I call this decision making or action taking applications. There's another you can see that there's system 1 and system 2. This comes from Daniel Kahneman's who won the Nobel Prize in economics from his work, going fast and slow, and where system 1 is perceptual, and the system 2 is cognitive, in my way of thinking, and you need both of them. So our human brain can immediately um, understand certain things, like a ball coming at you and you duck to make sure that ball does not hit you. But then human also, that is system 1, but human also takes deliberative um, decision making. Plants, I want to apply for a top a very good a good university for my PhD, working under a top professor. Well, that's your longer term plan, and make series of steps to go there. So um, this new symbolic AI would have a lot more play in combining the things that happens for this different kind of task to make a stronger task. And just like how human brains uses both of them. A slightly technical slide, but what I'm going to here say is overall there are many ways to combine um, the statistical techniques, the neural networks with knowledge. And the knowledge, by the way, can also not only be in a form of knowledge graph, but in logic rules, for example. There's also something called physics inspired, neurosymbolic AI. So uh, here there are a whole bunch of specific algorithms, and some of them are developed by my team, and there's some by others. And I have other keynotes that go that specifically discuss and compare these algorithms and give you insight into how knowledge is used to modulate the attention mechanism or loss function in the neural network. But there are uh, we once we classified these algorithms in shallow infusion, semi-deep infusion, and deep infusion. There is also a fourth kind which called knowledge elicitation. Now, here what happens here is that you create your feature abstraction layer from the data, and from the knowledge graph you create representation for knowledge processing and understanding, and then you combine in multiple ways. That plus sign here stands for many possible techniques, and then you figure out a way to use the knowledge appropriately in many different ways. That is the plus sign. And then you may have to make multiple queries, combine them. So there is a term that is becoming popular these days called agentic workflow. So you may be able to have series of activities you do to get those results that you want to, let's say, do for a doctor to develop a treatment plan or diagnosis plan using AI. So here is one algorithm that we developed. Is called TDLR, and it's an example of semi-deep infusion. And the bottom, you'll see that there is a self-attention matrix A, and then there is B, which is the knowledge semantics encoder. So that is coming from the knowledge graph. And then there is a matrix operation that combines the two. And then that is the one that drives so basically changes some behavior in the neural network. And then because of the infusion of the knowledge here, you can see on the bottom right, the system understands variety of terms that relate to World War One. The terms may have very different representation or syntax, but the system is able to understand that these terms mean something same. But and the improvement, as we show in the paper, is largely due to the fact that we are adding the knowledge to the traditional generative AI techniques. So obviously I'm not going to go through these details in the paper, but you can see that there are two interesting takeaways from our work. Knowledge context leads to performance gains with similar models. So these are models of similar size and all that. But knowledge context leads to performance gains with smaller models and smaller data set also. Even with the smaller data set and smaller models, we can compete with larger models. Right? That so these but large and TDLR based comparisons. So that kind of things you can do. Another thing that we do very well, that you can do very well, is that um, here on the left hand side you see the knowledge relevant to depression, and if you use a, let's say, clinical T5 model, and try ask it to explain how you know what is the reason for a particular classification, um, then and what are the depression signals that is in the text. It shows you that those red text, but they are not very meaningful for a clinician, for a decision maker. Instead, um, on the bottom in this green, we show the texts that are far more meaningful, like feel lost. So, and there is a PSQ9 concept of feeling hopelessness, with corresponding SNOMED term and such. So the system understands that and maps, the text to the concepts that are relevant to humans, like in this case, clinician. Um, now, for solving decision support assistance, what we argue is that we need to use data, we used to need to use knowledge, and we need to use human expertise, um, and that also not for just improving the quality but also explainability and safety validation to feel this system in the real world. We want to also have engineering benefits like reduced parameters, lower computational cost, and lower energy use, and then other business benefits. So as we started looking at some of the substantial applications, we found that there are many expectations and requirements for any system, for an AI system, for so that you can really far, consider this AI system to be robust, to be uh, more intelligent, and to be trustworthy. For all that, you see all those hashtag items. Those are all the items that um, you know we need to address before we can really have this so-called, what we call as robust, intelligent, trustworthy AI system. And we have done work on most of them, and the remaining one, is a work in progress. So it's a very exciting research area. Each of these hashtag item can be a subject of a PhD dissertation. One of the students just did her PhD proposal defense on analogy as an example, and another did already on causality. So there are a bunch of articles that I mentioned. You can get the slides, Google the titles, and get to them. And it's a very exciting research agenda. But it's very important to sit back and ask how much of this is supported by the best of the generative AI system today. And the answer would be they largely suffer. They are largely not prepared for all of this. Now, for that, now what I'm going to do is to show you an application. The application, uh, um, we have the important thing that I want to convey to you is that the real world application uh, that have real value, such as value in making a decision or taking certain action, are inherently a lot more complex than, and particularly enterprise application, a lot more complex, and have required a lot more, guarantees in terms of those robustness and trustworthy features, that compared to, let's say, what Gen AI system can do. So the AI needs to evolve to support them. Let me play a video. I'll play this long video and then one short video. So let me see. Can you hear? I hope you can hear.
Yes, Professor C.
So the video content is not audible or visible.
Video content is not audible or visible. Okay. Uh, I don't know if anybody knows setting.
You might have to present your entire screen, sir.
I'm presenting the. Oh, am I not? I'm presenting the screen, but let's see. Let me one try. Mm, mm,
Yeah, you might have selected the window,
okay, let's see.
presentation window. Huh.
Is it working now?
No, sir.
Yet.
Professor, Singh, probably you might have to like stop presenting and then start presenting again with sharing the whole window screen. Sharing the entire screen.
Let me see. Yeah, no, I'm sharing entire screen. So I'm using this here on the bottom right, this thing for entire screen that I'm doing.
Okay.
Mm,
So maybe there's a link over here which says please play on YouTube. Do we like?
let me try that. Let me. Where do you see the link on YouTube? Playing on YouTube?
I see it at the bottom of the slide.
Oh,
Probably.
slide. Okay, okay, okay. Yeah, that's what we should do. Right, right. Um, mm, Let me do this. Here it is. And um, any success?
Not yet.
Okay. Okay. So it looks like uh, the in the Meet. I know this works in Zoom, but in the Meet, I don't know how to make it work. Um, uh, oh, okay. Here's if anybody wants, I'll put the link in the chat, and you can see whether you are able to.
Yeah, that should work.
Okay, I'm going. Yeah, where is the chat in call applies? Yeah. I don't see chat option here.
It's next to the people icon. There's a like a chat box, bottom right.
Yeah, in this. Let me see.
If you want, you can send it to me through mail also. Maybe I'll open it up through mail.
Let me do that. Okay, I sent it, and I'm going to continue with the presentation. We'll play the video a little bit later. So, are you able to see my slide right now?
No, sir.
No.
No. Okay. All right. So hopefully you can see the slide now, right?
Yes, it's coming up.
Okay.
Yes.
So
Every meal impacts your health. So
Oh,
why
the
not?
video is working.
Oh, okay, okay. Let's then go ahead and play the video, and we'll. I'll stop sharing.
No, no, you when you played this, I think it was like visible to us.
Oh, okay. Let's see.
Yeah.
What is the time? Let me do short form video. Short video.
Well, now we cannot hear Professor Sit.
Okay. Okay. Let's move on. We can play at the end.
Right.
You will see the slide, right?
Hello. Today, we will be presenting a demonstration of the Allure Collaborative Rubik's Cube Solver. Our system consists of an
Hello.
automatic
Hello,
solver
everyone.
Today,
Today
I'll
based
be
on
we'll
temp
presenting a
reinforcement learning
demonstration of
Okay. So here is a. You remember earlier I was talking about. You're able to see my slides, right?
Yes, sir.
So earlier I was talking about how do you get meaningful insight into how let's say why the AI system says something or recommends that this is the answer. Here you can see visually that on the text, which is a text um, from Reddit, we are connecting back to the knowledge graph about depression, and here you are able to map the terms into and the terms you see they're not syntactically the same term, they are semantically related terms, and by being able to map.
So we cannot hear you.
Oh, yeah, now.
Yeah, there's some background noise. Anurag ji, can you please mute yourself?
Okay, can you hear me now?
Yes, sir.
Okay, so what you're saying is that the system is able to understand how the what are the concepts in the knowledge graph or human knowledge that is mapping, and you can see there's not just a syntactical mapping, it is a semantic mapping. Here there is a process knowledge or a knowledge coming from CSSRS. This is one for suicidability, and here given a text, uh, you are able to mm, answer the questions: wish to be dead, non-specific active suicidal thoughts, and you're making the system interpretable for clinician and patient. So for example, compared to LLM, using the kind of models that use the knowledge, you get far better results. And even I would say that 70% result is not yet um, good enough, but I think it is getting there. um, a very important example here. You see that earlier there was an example where a chatbot said you die or you should die, that kind of thing, right? Very unusual, a very unsafe interaction. So here is an example where the chatbot asks or co-pilots asks, do you feel nervous? And human answers, something, and then the chatbot has to ask multiple, other questions based on that answer. Here, the chatbot needs to understand that a certain question could be unhealthy and hence unsafe. So in this case, because of the use of knowledge that involves this what we call a safety check. So knowledge infusion using medical questionnaire, that technique that we have developed, you would understand that self-destruction is something you want to talk about. So it will ask the questions that are clinically safe, right? So this is a very important part on capability that the system need to have. Analogy is a now one of the things I mentioned was robust, intelligent. So analogy is a very important capability. It's critical for designing more intelligent AI system. It is useful for as a educational pedagogy. We often explain things with analogy, and it also supports innovation where you can transfer knowledge from one domain to another. So um, there are many types of analogy, and we define a taxonomy of analogy from lower level to higher level, and then so here is that uh, layers of analogy or taxonomy of analogy, starting with simple lexical analogies, syntactic analogies, or sentence level, semantic analogies, and then pragmatic analogies. So here, something on the cyber security text is mapped to Trojan horse related text. So you can use something from mythology to understand about cyber security, and it uses a lot of different it has a lot of different components: statistics, syntax, semantics, and pragmatics. So here is an example of taxonomy, and it has a number of concepts. For mythology, you have all these concepts you can see on the right hand side, and all the relationship you see, and the cyber security has similar things, and your job is to map the two and make sure that this is a comprehensive, complete analogy.
कटरे था कहने का घर पहुंच गए होगी मुझे लगता है ये उसी गाड़ी तो नहीं है
So something like this cannot be done without having the knowledge, right? So and there's a lot of detail that I'm going to pass now. I see the time. Okay. Another very important area is causality. So LLMs cannot reason beyond correlational pattern in the data. So that cannot be a true causality. So so this kind of things is very critical, and machine learning models are trained on observational and correlation data and correlation, but they don't get through causal structure. So it will be very difficult for them or impossible for them to identify unobserved, rare, anomalous, out of the distribution events. So we are developing this causality thing, because a next generation of causality where we can incorporate a whole variety of knowledge, perhaps of space, time, also together to support this. So current AI fail, in causality. Let me, they have a hard time distinguishing between correlation from causation, and they can't reason beyond data, what they have. So in the causal neurosymbolic AI that we have done, we use causal representation and knowledge graph to create this so-called causal neurosymbolic AI. And then you can also do the reverse, where you can use symbolic representation and infuse that knowledge into Bayesian. So on the left hand side is the Bayesian network, into the traditional Bayesian network, and make the system smarter. So here is one example. Here you see the smart manufacturing rocket assembly. You see the sensor data it will provide. Now you can see that there are a whole bunch of ontologies or knowledge graphs that are necessary to make sense of all that data. So traditional technique would be to use this data and apply AI to do your causal AI. But here what happens is that you are applying the knowledge to make the data more meaningful by labeling the entities in relationship. And you can see there are dynamic process ontology, there is a scene ontology, there is a causal ontology, and then there are existing general purpose ontologies. All of these are used to create a knowledge graph, and then on that knowledge graph you can do the queries. Given a no-nose anomaly, which frame and assembly cycle it is associated with, right? And from that you can get very much more meaningful information from your data. What happens is that the traditional causal AI methods will give you all these links, but you would not know the links and the meanings for the links and when you should traverse the link. So what we have to do here is to make those links meaningful and then traverse in context to really get a deeper understanding of what's happening and why something results into something else. Okay, so I'll just leave it at that. Another example is scene understanding in autonomous systems. So in this case, again, what happens is, suppose you get a ball on the street in a neighborhood. Now, a traditional AI model or genetic AI model will see the ball, but a human would reason that if it's a ball, there is a possibility of there's possibility of children around. How would you get that? Well, again, that kind of further intelligence in about this understanding the scene comes from the use of knowledge, and there's a lot of work that we have done in that area. Um, so here it shows that there are a whole bunch of issues in scene driving, and that the use of this knowledge graph and neurosymbolic AI technique improves upon all of those things. So in the MTSS, there is this 3-tier system. So thing to keep in mind is that many of the system, in this case behavioral health system, are pretty complex. They are related to let's say providing behavioral mental health support to school children, and it involves a whole kind of community of people. It involves family, counselors, administrators, and educators. And counselors may be a school level counselor and district level counselor and a nursing person. So they have different jobs to be done, and that there are different paths to supporting somebody. It may be a tier 1 support where you have general core instruction, your tier 2 support where you are doing targeted interventions, and tier 3 support where you do intensive one-on-one physician to patient interaction, right? Which of the interactions should be offered to which student for at what time? These are all the complex questions. So here is the view of the MTSS system, and it has many components, and it maps to some of the needs. Here you can see I'm showing that there is a there is a need for grounding, there is a need for alignment, there is a need for instructability, and there is a need for reasoning on the top right. All of these are necessary. These are the kind of things that we have not seen generative AI systems currently do, and that's what we need to do because these are real world applications. You need to support them. Okay, here there are a lot of functions that you have in the middle, and all right. Next is a food computation personalized nutrition application. So it's a very complex domain. It needs multi-contextual reasoning. I'll explain that. High-stake domain that requires robust and trustworthy AI, and you need user-level explanations. So you have an image. This is the food that the patient or somebody is nutrition seeker is interested in analyzing, saying, can I should I eat this? And to do that, this image, there's all these issues of image and the segmentation and understanding and all those things that we do, and their generative AI is very useful. And some of those tasks can be done very well with image processing system of today. But then there is a lot of other things to be done. So you need knowledge sources of various kinds, and you also need the recipe text and images. In this case, so can I eat this requires a lot of reasoning, and it may be that, well, you have potato in this, and it has a healthy carbohydrate but high glycemic index. Canola oil is undefined. Quite likely, it is canola oil. Undefined is a good fat. Deep frying, trans fat. Potato plus frying is vitamin A and C lost. Allergen, and you can see the sources of the knowledge: WebMD, US FDA. Allergens, dairy-free, nut-free, and daily value calorie within limit. And then you get the results, and it says, well, you can have alternative recipe, or you can have revised recipe. Say, do air frying instead of deep frying to improve the um, to make this more acceptable for your nutritional need. So many things are involved in this process, and here I'm showing you a piece of that. I guess this slide has too many things to discuss here effectively, but what I'm want to make, the point that I want to make here is that you have multimodal processing. You have knowledge graph that have knowledge related to all of these components. You have disease specific knowledge graph. You have cooking taxonomy. You have ingredient substitution knowledge graph, and you have understanding of all of those cooking process, and then you can see the model there. So entire system is quite a bit more than just what the model is. So finally, you have the model that will do certain computation, and then support the application. Okay. So and then there's yet another thing about attribution. Can you say what is the basis of, what is the source of the information that AI system has sent? You remember that case where a lawyer asked ChatGPT about creating the legal brief, and that and the AI model just made up all the citations. Well, that you want to prevent that. So you want to be able to attribute exactly what are the source of information that you rely on, and that is the and here we show how how using the neurosymbolic approach we can address this problem. Okay. So now I'm going to make now final points, that we talked about value-inspired neurosymbolic AI, and there are other various terms: human-inspired AI, civilizing AI, constitutional AI, and they vary a little bit. But the human-inspired AI and civilized AI are the terms that we have coined. So there are many values, that social values, cultural values, individual centric norms, and if you to make AI systems a healthy component of human society, you really need to pay attention to all of those. That's what we discuss here, and that then there needs to be effective way to combine those values. So one example I already discussed was about the safety, that you do not want to ask about self-destruction. But there are many other example I discussed was explainability, and explainability for a particular user or class of users. And then there are many other types of value systems that you have to bring in to really create a useful um, an AI system that fits into the human society. There is a broad outline of that here. So these are my students and my immediate team, and a lot of sources for support here. Okay, so with my budget of time, we have a few minutes left. In case you guys want, so we have two options. You can play one video if you're able to do that.
Yes, yes.
And, yeah.
Sure. I can present the
Okay.
video. I can play the video.
Yeah, please.
Okay. Is my screen visible?
Yeah.
Yes.
Why not make it?
I'm not able to hear, but hopefully others are.
No, sir.
No, it is not audible actually.
So was it visible, Nikunj?
Yes, it is visible but not audible
Not
exactly.
audible. All right.
Yes.
So maybe let me try this one also. Just, just check this one.
No, not audible.
Okay. If that's not the case, we can we can send the share these slides,
Yes.
and I'll send the link to Dr. Singh, and then
Yeah,
Yes. Yes.
I'm also like putting in the links in the chat box. So anyone who is interested in looking at these videos, yeah, I put in the links in the chat box.
okay.
Yes. Yes.
So the floor is open for participants to interact with Professor Seth, and if you have any specific questions, participants, you can unmute yourself and interact with Professor Seth.
Yeah, can I go ahead with a question?
Yeah, sure.
Namaskar, sir. Sir, so I am a research scholar and I'm beginning to work in the same domain as yourself. And uh, I have a question related to whether what is your opinion on detectability of AI generated text? Since you showed us the paper and the index, uh, do you think it's really feasible, or do you think there be some approaches that we should take in order to make it? Maybe we can narrow it down to some domains or something where it becomes feasible. So, what is your take on it?
So basically, watermarking techniques have to be developed. We are working on those techniques. Uh, Particularly, the research associate professor Amita Das is coordinating those effort, and we think that we can develop some watermarking techniques to so that if the image is generated by AI system, that it will be watermarked, so you can say it is AI detectable, AI generated. But in the next sometime, I do not think that it will be possible to detect. Right now, I do not think any company has a solution for detecting whether the text or image or video is AI generated or not. So maybe those techniques will evolve. So it's a very good research topic. So if you're working on that, great. Please do work on that. But it's not going to be easy. But here, for example, you'll see a whole bunch of effort has been made in watermarking.
Okay. Okay.
Any
Yeah.
other
Thank you,
questions?
sir. Yeah.
Um, Dr. Biswa Senapati has a question, Professor said, that for data imputation in the dataset, GAN and LLM are used by the researchers. Which one is better?
Um, say something more about what do you. I mean, um, I, I really don't know. Uh, i- that's something. Um, yeah, not something I would be able to guide you on. I mean, first of all, when you just say even LLM, I mean, there's such a wide variety. Uh, are you? I assume you're talking about transformer model, but um, all of the LLMs are going to create high dimensional space. Yeah, the number of dimension will change, the number of you know. So the complexity, number of layers will change. All of that will be done, but in the end, going back to what the data was is not possible. It's just the nature of the technology. I mean, the same way that uh, hallucination is a artifact, is a feature of this technology. So unless and you really don't have control. Uh, all the top AI researchers will also say that yeah, it's largely a black box. You don't really know exactly how you got to that. So I doubt that you can do this well.
Um, we thank you, Professor Seth, for your all the different aspects of AI that you let us know about, all the challenges which are associated with AI models, and you told us about how important it is for fact verification of the misinformation that can be spread by these AI models, the hallucinations in AI, what are the aspects of value inspired AI. So you have like given us so many different flavors of AI in your talk today, and I'm sure that the participants will benefit from all these inputs that you have given them in their future research. We really thank you for taking out time to interact with all. Thank you very much, sir.
Okay, thank you.
Bye bye, sir.
Bye.
Okay.
Um, uh, Dr. Nikunj, Dr. Hemant Agarwal has joined us. So our next speakers is already here in the panel. So can we Like you can introduce him and we can start the next session.
Yes, absolutely.
Yes, okay. Welcome to you, Dr. Hemant.
Hello everyone. Hi.
Hello. Hello, sir. Okay, so just let me share my screen. Okay, so okay, good evening, everyone. So, welcome to the fourth session of ATAL FDP on deep learning for vision and language. So, we are honored to have with us Dr. Hemant Kumar Agarwal. So, who will be the speaker for the topic model based deep learning with applications to MR trajectory optimization and CT kernel synthesis. Sorry. So, Dr. Hemant Kumar Agrawal is working as a staff scientist at GE Healthcare, Bangalore, India, with broad research interest in inverse problems of physics in SPAT deep learning. He received his PhD in computer science in the year 2016 from Indraprastha Institute of Technology, Delhi. As a postdoctoral researcher in computational biomedical imaging group at the University of Iowa, USA, he developed novel algorithms for accelerated parallel MR image reconstruction that combine the power of recent deep learning techniques with the traditional model-based algorithms. He has published several research articles in various top-tier journals and conferences, including IEEE Transaction on Medical Imaging, IEEE Journal of Selected Topics in Signal Processing, and magnetic resonance in medicine. He has served as a reviewer for more than 150 articles for various journals. He received a Distinguished Reviewer Gold Medal Award in IEEE Transactions on Medical Imaging. His collaborative research on parallel imaging got the Best Machine Learning Paper Award in ISBI 2019. He was nominated for the Emerging Investigator Award at the Imaging Elevated 2020 Symposium at the University of Utah, USA. So I now invite Dr. Hemant Kumar Agarwal to take over and begin the session. Please, sir. Thank
So
you.
thank you for the kind introduction. Sure.
Welcome, sir. So,
Okay.
sir, you can share your screen and you can
Yeah,
start
I'm
presenting.
just trying to share. Yes, 1 second. I hope my presentation is visible.
Yes, sir. It is coming up now.
Okay.
Yes, it is visible. Yes, visible, sir.
Okay, sure. So today we will be talking about a particular kind of deep learning architectures called model-based deep learning architectures. So I'm going to show the applications in MR image reconstruction and CT kernel synthesis, but the architecture is very much open, can be used in any other problem, basically any linear inverse problem. The way we had developed it is applicable to any kind of linear inverse problems. Okay, so what we will be discussing today is, firstly we will start with MR image reconstruction problem. Like in MRI, it is very wide area. So we will just check what is like broadly what is a MR image reconstruction problem. Then we will see how this particular architecture, why it is needed, and how it is developed and which specific problem does it really solve. How does it help us? Okay. Then we will.
Miss Kritika, please mute yourself. Miss Kritika. Sorry, Dr. Hemant. Sorry.
No problem. So yeah, now it is better. Yes.
Yes, yes.
So then we will. So once we develop this architecture, then we will see different problem, which is called MR trajectory optimization. So it is about like when you are on a scanner, you scan some patient, you scan data at every location. But which location do you really select? So you run something called a trajectory on the scanner, and what is the role of that trajectory. We will briefly see and how we can optimize that using deep learning techniques. Then we will see one another application which is called CT kernel synthesis. We know CT images are acquired with different kernels. And if you have to change from one kernel to another, how you can use this particular architecture or this particular framework and develop a different architecture. So once you formulate an optimization problem, what else you can do with it? So we will see those details. We will see one particular specific solution called an analytical solution, very simple without any iteration, how it solves the problem. We will see its limitations. Then we will go into something called a Newman architecture. This is another variation of a model-based deep learning architecture that naturally occurs from your by when you solve an optimization problem, its architecture naturally occurs. So how it does it helps us in solving a kernel synthesis problem. And we will see some results and conclude. Okay, so let's start with MRI. So this is a particular MR scanner. So this is a 7 Tesla scanner. So when a patient goes here into the scanner, so there is a phenomena called a nuclear magnetic resonance. With respect to that phenomena, you get the MR images. Okay, so this is at a very high level. Okay, so what does this image represents? So the pixel intensities, every single pixel intensity, it represents the strength of transverse magnetization. It is a particular kind of magnetization in the transverse direction, orthogonal to the direction in which your patient is lying, orthogonal to that. In that particular direction, what is the strength of magnetization? Every single pixel in this image represents that thing. Okay, so but what is the benefit of this MR? So we know MR has several benefits. One is being non-invasive, which means you are not making a hole inside the body or sending a camera there. No, you are just sending the patient into this and you're not touching the patient, and you take the photos of the inside the body. Okay, so this is non-ionizing, so it doesn't use any ionizing radiation different from the X-ray or CT. So it uses simple radio waves. Okay, so this is like non-ionizing, which is like a great thing. So if you are sit inside the scanner for 15 minutes, 20 minutes, it is really good to have a non-ionizing rather than ionizing. It gives you very good soft tissue contrast. So inside the brain, when we look at, so you want inside not just the brain, entire body. So anywhere there are like so many soft tissues, so you want to contrast one thing from the other thing. So MR has this benefit that it gives you very good soft tissue contrast. So whenever you want to see inside details or distinguish between tumor and a normal tissue, it is very good to use the MR. Okay, but MR is often criticized for being a slow imaging modality. So compared to other things like X-ray, CT, it is a slow imaging modality. If X-ray takes like 30 seconds, it takes like 15 minutes, 10 minutes based on the exam to exam, protocol to protocol. So one particular problem. So now that we know it is a slow imaging modality, what can we do about it? So definitely we want to accelerate the MR acquisition process. So how we can accelerate the MR acquisition? So what is the benefit of accelerating? Why we would like to accelerate? One is that definitely we want to acquire the data as early as possible. So that has several benefits. It leads to patient comfort. So definitely, like if some patient has to sit for 30 minutes versus 15 minutes, so it will definitely give the comfort to the patient. It will definitely reduce the acquisition cost, because in one day then you will be able to do more scans. So per scan the cost will reduce. So you will utilize the scanner more, the MR machine, you will utilize more. So instead of 10 patients, maybe you are able to scan 15 patients or 20 patients in a day. So you want accelerated acquisition. So another thing that is more important is the artifacts caused by the motion. So if you accelerate the acquisition, so suppose a patient went into the scanner because patient is not well. So definitely he or she can move little bit. Okay, so if the patient moves little bit, so the scan will get a deterioration, or there will be severe artifacts inside the when you reconstruct the image. So you want to reduce the motion artifacts. So if you do accelerated acquisition, it has a impact that it will reduce the probability of your motion artifacts. Then there is something called as artifact due to signal decay. So as I told you, every single pixel in the image. So if the strength of magnetization decays, you don't have a very good signal, which means signal to noise ratio is low. So you have noise and all. So artifacts will be there if the signal has decayed too much due to the long acquisition. So you want to accelerate the acquisition. So therefore, now how can we accelerate the acquisition? Definitely there are several methods. Definitely there are very good hardware-based methods. But today we are going to look at the software-based method. What can we do inside a software? Okay, one particular technique is called the acquire fewer samples. So you, rather than acquiring all the samples, you acquire the fewer samples and then try to reconstruct the image. So that will accelerate the acquisition. So I hope the acquisition problem statement itself is clear. If anybody has any doubt, please ask. Feel free to interrupt in between and ask the question there, and then that will be good for everyone. Yeah. Okay, so now let's look at this visually, how it is this problem. Okay, so you have a patient that goes into the scanner. Okay, so now we are just introducing some of the notations. Okay, so you represent your patient or the particular part of the patient that you want to scan. Then what you do, you represent that as a X. You don't know what it is. You represent your acquisition process inside the scanner as a operator called A operator. This represents everything that is happening in the scanner. Scanner has so many things happening. It has its trajectories. It has Fourier transform. It has multiple coils. It has a undersampling operators. Everything has been represented using the operator A. And what you do, you take all the samples, which means using this for just a linear equation, you take at every single pixel, you acquire the data. Now, when you acquire all the samples at every single location, so this is something called the K space. It is also called the measurements, or this is what we get out of a MR scanner as a output. Okay, then you use your algorithm. So something called, you use inverse Fourier transform, because at every single pixel you have the value. You can simply do the inverse Fourier transform and get something image. So this is our image that we get here. Okay, so this is our reconstructed image from the fully sampled data. Now we talked about the taking fewer samples. Now if we take fewer samples, so now wherever it is black, which means you didn't acquire the sample. So this is a specific kind of trajectory called a variable density, which has a fully sample center, but you have less signal everywhere else. Okay, so now if you acquire fewer samples, then you cannot simply use an inverse Fourier transform. You have to use something called a reconstruction algorithm. That, and then you expect from your algorithm that it should give you a same image quality as the fully sampled data. But what you have done, you have taken fewer samples. So definitely this one is a accelerated scan. So from this accelerated scan, this is good that you could accelerate by taking fewer samples. But now you need a reconstruction algorithm. How you can reconstruct? In this case, it was a simple inverse of the Fourier transform. But that is, you cannot use anymore. Now, if you have lesser number of samples, you need a reconstruction algorithm. So what kind of reconstruction algorithm can we use? Okay, so there are so many different kinds of algorithm. Definitely the classically or right now also in the scanner are the iterative algorithm. Definitely there are deep learning based algorithms that are coming up, and so many are on the scanners also. So we will briefly see what are the different kinds of algorithms that are available to reconstruct the data. So let's see that one. Okay, yeah, if anybody has any doubt, just please let me know. Okay, so like you have a data that is coming from the scanner. So these are called your measurements, and this is what you are interested in, which is your reconstruction. Okay, so typically, like classically, you had the compressed sensing based solution. Just before deep learning, the compressed sensing was there. So you solve your linear inverse problem of this format. So you have, this is what you know. Y is the sample that you acquired, so you know this. A operator is what you know. Okay, so this is your, this represents your like a Fourier transform or whatever way you acquire the data. It has coil sensitivities. It has your undersampling mask if there is any, or any other information about the acquisition process. All, everything is embedded into the acquisition operator A. Then this is rho is what you are interested in. So this become a linear inverse problem. And there are many ways. So typically, how do we solve? We formulate it as an optimization problem. So what we are interested in, we are interested in rho, what we have y and a, and then we have something, this is something called a data consistency. What it means? It means the data that we have acquired, we don't want to deviate too much from there. So original data that is coming from the scanner, we want to preserve that. Little bit of deviation is okay. So you are minimizing a standard deviation of the noise here. Okay, y minus arrow represents the noise, and what you are doing, you are minimizing the L2 norm of the noise, which is equivalent to saying you are minimizing the standard deviation of the noise, which means you are minimizing the noise, which means you are minimizing the error in the measurements. So you measure something and you don't want to deviate something. But now the problem is, because this is a undersample acquisition, you have infinitely many solutions. When we have infinitely many solutions, we want to narrow down the solution. How do we narrow down the solution? We always narrow down the solution by using some prior information about our data. In this case, what we are interested in, our data is the image row. This is what is unknown. So we put some prior information about our image. What kind of prior information we can use? So we can use anything like we say total variation is minimum, or wavelet based sparsity, or plug and play denoiser, or there are many different variations of these that we can use. So one point more, like this step is also called imposing the physics constraint here. So what do we mean by the physics constraint? Physics of the MR has been represented in this equation using the forward model A. Whenever you explicitly utilize your forward model equation in your either architecture or the loss function, then your network is a physics inspired neural network. Okay. So, but what is the challenge with this kind of approaches? Solution really depends on the choice of prior. So because these priors are the fixed priors, hand wavy, you define a particular kind of total variation or a particular kind of sparsity prior, like not necessarily wavelet, anything you utilize. For example, DCT based sparsity you can put. So you can use a dictionary learning based sparsity you can put. So, but those are like a fixed kind of prior. So you want a solution more generic. Okay. So if you just look at this equation a little bit more carefully, so this is the kind of linear inverse problem in general. Okay, this is not necessarily related to your MR acquisition problem. Suppose if you have an inverse problem like image denoising problem. So A operator become identity in that case. So you are just solving y is equal to x plus n. Okay. If you have a suppose image deblurring operation, in that case A become your blur operator. Everything else remains the same. So this is a very general linear inverse problem, and this is the problem that is what we are interested in solving. Okay, so there are many kinds of prior. The most simplest one is the Tikhonov regularization. It is just you say that energy is minimum. What does it mean? It just saying that every pixel you take it square, then do the square root, or you don't do the square root. Then you say that this is the energy of the signal, and signal has a lower energy. You are then this is called a Tikhonov regularization. So that gives you a decent solution, like a starting good solution, you can say. Okay, or you can use something little bit better than that. Definitely it gives you better solution, yeah, and that is a total variation. So total variation, what does it do? It calculates the gradients and then minimize the norm of the gradient. Okay, or you use like a L1 regularization or L0 regularization, sparsity regularization, or more recently people have been using the CNN based regularization. Now there are so many variations of the CNN in the market. The problem formulation remains the same, the framework remains the same. You utilize different CNN architectures in place of R here. So different kinds of CNNs you have, and generic in general, how do you solve this problem? With the different architectures you get different solutions, and you have so many priors now available. You don't necessarily have to put a L2 regularization here. You can minimize the LP minimization like a general P norm with P between 0 and 1. So it gives you a lot of possibilities here if you utilize this kind of prior. So this is the general regularization techniques that we use to solve the linear inverse problems. So I wanted to give you one quick example of how does the specific kind of prior look like. Okay, so this is the total variation example. Okay, so TV, what does it do? You calculate the, suppose you had a clean image. Okay, so this is some tiger. So you take its gradient in the horizontal direction, which means you subtract every horizontal pixel from each other. So first pixel you subtract from the second pixel, from the third pixel, second pixel from the third pixel from the fourth pixel, like that. So you get an image out of that. That is the called horizontal gradient. Now you also calculate something called vertical gradient. So that is GY. Okay, so this is GX, this is your GY. Now then you When you do this TV total, then this is what you get here. That is the total variation. That is the total gradient that you get. So here you can notice that like this whiskers and all, which is visible in the vertical, not in the horizontal one. These ones. Okay, so different features aspect to, so anything which is horizontal will be visible in one, completely vertical will be emphasized in the other one. So this is just the two filters that you used here, two filters. Now imagine your CNNs, which gives you so much power. They have so many filters in your CNN architecture, so they are much more powerful than a single total variation regularizations. Okay, but these were giving you pretty good results before deep learning. Okay, so this is worth knowing. So then there are other kinds of priors which are like sparsity promoting. What does sparsity mean? So sparsity, even today also sparsity is used heavily in the convolutional neural networks, and people are still exploring it, how it is useful. So what does it mean? It means that you have some data. What you do is you represent it in some transform domain such that it is sparse. Sparse means like here I am plotting one signal, which is like having 200, a vector of having 200 by 1 size, out of which only 10 values are non-zero and rest are all zero. So all the values are zero except the few non-zero values. So that is the meaning of sparsity. And you can put that most of the images have a sparse representation in some transform domain. So you can always explore the sparsity based priors. Okay, and you can use them in conjunction with the CNN architectures, that how you will formulate the problem statement which suits your particular application. Okay, so these are there are different kinds of algorithms that exist to solve this kind of optimization problem. Here I have simply used something called SPGL1. So this is a one particular algorithm that I use to solve, like if your data, original data is the red one and the L1 solution is the green one, you can see they completely overlap on each other, which means the solution is just accurate. So I use one particular solver, but you can use anything to solve for this problem. Most common is the ADMM and all. Okay, so these are the different kind of, the problem with these approaches is they have a very high reconstruction time. This is what deep learning is helping us with. Deep learning gives us very less inferencing time. Of course there is one time training time, but after that once you deploy the model, solution comes very fast. So that is where we get a lot of benefits from the deep learning. So definitely deep learning overcomes our these two problems. One is the prior, prior being very specific. Now you don't have to rely on a specific prior. You can learn your prior from a huge amount of data, which means it becomes a very generic prior. A prior which allows you to select, narrow down your solution. So ideally you had infinitely many solutions. You wanted to narrow down your solution. What you rely on? Prior. Now, if you learn your prior from the CNN, that gives you huge power, because you can just learn anything from any given data set. Uh, you don't have to put some constraint or assumptions. Okay, my images are always smooth. My images are always sparse. You just remove those constraints, so it becomes much more generic and powerful at the same time. Okay, so how do we typically use it? So in particular, in this example, our running example of MR image reconstruction, what is coming out of the scanner is your Y. That is your measurements. When the data is coming, what you do, you do something called a zero field reconstruction. Zero field reconstruction. Okay. And what does it give you? It gives you an image. So you, this is a simple one line operation. So this is the analytical, just simply the Hermitian of the operator. Whatever operations you had in A, just do the Hermitian of them, apply that, and you get the image. Once you have this image, and suppose you also had a lot of pairs of the corresponding images, like this is your undersampled data, this is your fully sampled data, you can always train a neural network from this image and get the output like this. So you can just, if you have thousands of images, you can train your neural network very well. So this is something called a direct inversion network. So network is learning how to do the inverse. So why we are calling it like that? So you had this problem, right? Y is equal to ax plus n. Y is given to you. You were interested in finding x. So from the y, you generated A transpose y. From y, and you generated A transpose y, and then you found simply x. So you learned the mapping using CNN. So which is equivalent of doing the inverse of x. So x is equal to A inverse y. So that inverse thing has been done using CNN. Okay. So that is why you can call simple direct neural networks which do a direct mapping as a direct inversion networks. Okay, they have certain limitations. One particular limitation is this is the solution that you get is not necessarily data consistent. What do we mean by that? Because you did not use the A operator explicitly anywhere in this process. You simply had this kind of images, and from here you learned this kind of mapping. You did not utilize, so CNN used what? MSC between them, and then or some loss function you utilize. You didn't explicitly utilize the information that you had available. So there is a lot of information about your imaging protocol that you had, or your call sensitivity maps that you had. So you can use a lot of available information about your A operator, and then you solve. So that becomes a data consistent solution. Okay, so in MR, so in medical imaging in particular, being data consistent is very important. So your deep learning model should not change your actual data. So this is true for in general all the medical imaging, whether it is ultrasound or CT or MR or whatever, right? So you want your solution to be data consistent, so that you don't change it. You don't want to mess up. If you just get some undershoot here, if you get an undershoot here in the image, what does that represent? That represents undershoot means a missing pixel that will represent a hole in the brain. Okay, so it is very critical to be data consistent. You don't want to change your original data too much. So that is why we are emphasizing how do we get a solution from a deep learning method which is explicitly data consistent, and we utilize a neural network only as a prior. Okay, so one particular good example which has been shown in the image reconstruction only is from this paper. This is the ISTANET, very initial paper on so utilizing the ISTA algorithm. ISTA is a sparsity based algorithm, iterative soft thresholding algorithm, and corresponding to that you had an architecture called ISTANET architecture.
Dr.
So
Hemant, I think
yes,
some Dr. Abhijit has raised his hand. Probably he has a question
yes,
for you.
please.
Uh, Sir, I have a doubt that in the previous figure, you have taken the input as y, then you have applied the CNN to that to estimate the x. Then the question is that whether the y is, if it is a vector, then whether you are going to use a one-dimensional CNN or two-dimensional CNN. Perhaps the input y is the measurement considered as vector. If you take different time stamps, then it will become a matrix. But for the time being, I think input will be a vector.
Yes, correct. So y is a vector, definitely y is a vector. Okay, so but what you can do, I said like y is a output of ax. So you applied your a operator on x, okay, to get the y. Suppose x is your image, that is what you are interested in. Suppose x was some 100 by 100 image. Okay, so this is your x. What is a operator? A is your Fourier transform. So Fourier transform will be your on the same, it is a 2D. If it is a 2D Fourier transform, output of that is going to be again 100 by 100. Okay, now it just not involve only the Fourier transform, it also involve undersampling. So you have some sampling operator, so which means which particular pixels in the Fourier domain you should pick up. So that is again your 100 by 100. Okay, so I'm sorry, 100 by 100 it is. Okay, so this is again a 100 by 100 matrix. So out of that, it is a binary matrix of 0 and 1. So if you are doing 50% undersampling, so 50% locations in the Y will be 0 and 50% location will be 1. But still, it will be a 100 by 100. Okay, so you get it right. So it is a undersampled matrix of 0 and 1, and it is actually a matrix form.
That
Now,
means we
when
are going to
yes,
apply convolutional 2D CNN.
yes, we will apply to see 2D convolutions. Yes, so once you have Y, you can simply apply a transpose operator on that to get an image. Once you are in the image domain, you can apply 2D convolutions. Correct.
Okay, thank you, sir.
Yeah, yeah. If any other question, please feel free to ask. Yeah. So we were discussing why the data fidelity term is important. Okay, so this is a good example. If you have a Ethernet algorithm, if you do not have a data fidelity term, you have a reconstruction output here. This is a one particular reconstruction network. This is another network which is called a ISTA network. ISTA network is a network which is a model-based deep learning architecture that utilizes ISTA algorithm, which is a very famous algorithm. Okay, it utilizes that particular algorithm to solve the problem. Okay, so there you see the zoomed version. So here you can see these boundaries. These boundaries are much more uniform here as compared to the middle one. So if you just compare these two portions, you can clearly see there is a benefit of imposing data consistency explicitly. Okay. Yeah. So we can satisfy the imaging physics. So basically this is all about the imaging physics. So imaging physics is representing using A operator. So how do you utilize that is what we utilize using model based approaches. So in particular, you solve the problem like this. So you do not completely rely on a CNN. You utilize CNN as a prior. That is what you are emphasizing here. So that you get a best of both worlds. You are using a iterative algorithm. Iterative algorithm by default utilizes data consistency. Okay. On top of that, earlier you were using some simple priors like total variation or sparsity. Instead of those priors, if you utilize a CNN as a prior, that will give you the benefits of all the properties of the CNN. But at the same time, you are solving an optimization problem, which is this like a minimization problem. You are not completely relying on CNN. You are also utilizing your data consistency. So this is called a model-based deep learning. So I would like to just tell you what is model-based here. Model-based means forward model. What is the forward model here? Forward model is this particular thing. This is your forward model. How do you pose your problem statement? If it is a denoising, deblurring, reconstruction, deconvolution, any kind of problem, many problems you represent as a linear inverse problem. So this is your forward model. This is your forward model. So anything which utilizes the forward model is a model based. Now second part is a prior thing. So prior is a deep learned prior. So that is where it is. Okay. So I hope that is clear. So that was our fundamental thing throughout this presentation. This is the problem formulation that we are going to use. Now this CNN priors, how do we actually realize them? Means like CNN output of a CNN is going to be image. Okay. So in this particular settings, we have utilized one particular kind of architecture, ResNet, which is very famous by now. So this is a NW means a noise learning. So output of the network is giving you noise. You add back, you have a residual connection here, this red one, which is going here. So that is giving you back the image. So here you have a image output. Okay. So this particular architecture, but you are not restricted to anything. Nowadays, you have so many architectures available. The best available, you should utilize that one. Okay, and then how do you formulate the problem? This is how you formulate the problem. So you have the first term data consistency as it is, but what is the regularizer? The network output DWX is your network output. So this is your network output. You want some solution X. So this is your solution X. You pass that through the network and you say the error between them should be minimum. So network should not deviate too much from the data consistency. This is what we are saying here. So the X which is coming out of data consistency, that X is this X. And this X and the network output, between them, error should be minimum. How we are seeing error? So this is this X minus DWX is the error, and minimize means you are minimizing the L2 norm of the error. Okay, so this is our regularization term. This is not just the only regularization term. This is one of the regularization term to utilize the neural network. But you can utilize some other constraint like L1 norm. You can minimize here. You can minimize LP, or you can pose it like a very different kind of X transpose DX, where D is your neural network output that gives you the weightage, how you apply on the X. So different ways are possible to utilize the neural network as a regularizer. Okay, this is one particular way that I had worked on during my postdoc. So this is how you pose the problem. Okay, so once you pose it, now you want to solve it. How do you solve this problem? Okay, so there are multiple ways that you can solve this problem. Okay, so this is the problem statement that we have. DWX, you understand, is the output of a neural network. W stands for the weights of the neural network, which means it's a parameter. Like you have a denoiser which has a parameter W. You can think of it like that. So W represents all the trainable parameters in your neural network. So clearly this has a this is a multi-objective. So DW is, you don't know what is DW and you don't know what is X. So you assume like, okay, at one point you know one, so you use alternating minimization. Okay, so you assume that Z is equal to the output of your neural network. Then this problem becomes a simple problem. So compared to the above one, this becomes simple if you assume Z is constant, Z is constant in this particular equation. Then you can simply take the derivative, because both are L2 norms. You can take the derivative. So F means this whole thing is F. This whole thing is F. Okay. So then you can take the derivative with respect to X. X is your variable of interest, your image, actual image. So the derivative is simply in this case -2 A transpose y minus AX. So yeah, there is a little bit of matrix calculus. So just utilize that one. So if anybody has any doubt, please write back to me. I can give you the pointers on how this has been derived. This is a simple matrix calculus, and you get the derivative like this. Now, once you have the derivative, then you can use the gradient descent. How you use the gradient descent? We know gradient descent is this particular equation. X new value is old value minus alpha times the gradient. This is our traditional gradient descent. Just put the gradient here, so you get a updated image. Now you can utilize this and solve your X here with respect to Z. So one time you solve for X, another time you solve for Z. So Z is assumed here constant. Assuming Z as constant, you can get your X as a solution. Everything else you know about this equation. You know alpha. Alpha is your just learning rate. Lambda is your how much importance you are giving. So you can make it either trainable, or you can use it as a fixed value, something like 0.05 or something works well. Okay, everything else you know, A operator you know. So you can solve it and you can get a solution. Or you use something called the conjugate gradient. Okay, in conjugate gradient, what you do, you put the gradient is equal to 0 and you solve for the normal equation. So this is your normal equations.
Excuse me, Dr. Hemant.
Yes.
Dr. Abhijit has a question.
Yes, please tell.
Sir, this DW is a second order difference matrix or anything else?
This DW, I'm sorry, this DW is a neural network. This DW is a neural network. What we are saying here, the output of the neural network should be very close to the output of the solution to your model-based solution. So if you go back to this equation, this is your DW. You see here, this is your DW. DW is representing your neural network architecture. It can be ResNet, UNet, any architecture. Okay.
Okay, thank you, sir.
Yeah. So you get a normal equations and then you solve the normal equation. So using model simple alternating minimization. So you have two steps. One is a denoising step. One is a conjugate gradient based data consistency. What is the benefit of conjugate gradient based data consistency? It can handle general solutions to your problem where A operator is not invertible. So many problems statements like diffusion MRI, parallel MRI, they do not have a operator which is invertible. In this case, you have to solve your data consistency step as a, rather than analytical, you have to solve them iteratively in a few iterations, like 4 or 5 iterations. So that is the benefit of using conjugate gradient based data consistency step. Okay, so this depends on your specific problem statement, basically how you formulate your A operator. In some cases, A operator is very simple. In that case, you have a very simple solution to your data consistency step. In another problem statements, it can be more complicated. In that case, you have to design how is your forward model. Based on that, you have to design your data consistency step. So now let us make an architecture out of these two equations. So you solve these two equations in few iterations, maybe like 10 iterations. You just iterate between them and you get a solution. So you start with some initial solution X naught. But what can be a good solution? Any solution. Suppose you assume there is no deep learning here. In that case, DWX is simply 0. Then you get a Tikhonov regularization. That can be your X0. Then you pass through, firstly, in iteration 1, you pass through the DW step. And then you pass through the data consistency step. So this particular operation is your data consistency. It is taking two things. One is a Hermitian y, which you are passing here. Second is zk, which is coming here, zk. Okay, so together they make a one single iteration of your alternating minimization algorithm. So overall, it is a optimization problem which you are solving using iterations. So this is your first iteration, which has two steps. One step is your denoising step, which is like a projection step. Second step is your data consistency step. Okay, and then you repeat this process k times. So k can be like 10 iterations, for example. And at the end of the kth iteration, you get your output xk. And that output, you treat it as a prediction of your neural network, and then on top of it, you will minimize your loss, whether it is a MSC loss, SSIM loss, combination of multiple things, whatever kind of loss. So this is your overall architecture. Okay. And definitely you share the weights here. So however, it is not a hard and fast rule. These are the different architectures. You can have like a unit architecture here. Then here you can have another unit 2. It can be unit 1, unit 2, for example. Or it can be the same unit. If it is the same unit, then this denoiser or a projection step becoming much more generic. So that has several benefits. Okay. Now you can see this unrolling improves our reconstruction quality. What I'm showing here on the y-axis, you are seeing the PSNR. Higher the PSNR, better is the output. On the bottom, you are seeing the number of iteration. What is this iteration? It is the iterations of your architecture, that k. So here, this particular experiment was done with the 10 iterations, which means if you use only one iteration, then do the inferencing with the gradient based or simple conjugate gradient. In that case, how much is the difference between the PSNR values over an entire data set? Okay, so you can see very consistently as you increase the number of iterations of the architecture, which means architecture becomes more and more complex. Okay, complex in the sense it is just a unrolling steps. How many unrolls you are using? If you use more unrolls, it is solving the algorithm, the alternating minimization algorithm more accurately. Thereby, it increases your accuracy. So you get even like 38, around 37 your PSNR at a higher iteration, and then it start to saturate here. So you can choose like 8 unrolls or 10 unrolls depending on how much GPU you have. 8 unroll, 10 unroll means 10 different unit architectures, 10 different ResNet architecture has been used in this particular architecture, but they can have the same weight. So number of trainable parameters will not increase. It is just the utilization, how they have been utilized. Okay, so yeah, if there is any confusion, let me know. So we can see the some visual results. So this is an experiment we had done using fast MRI dataset. We did like a 4-fold undersampling. I don't remember, maybe 6-fold undersampling this one. If you use gradient descent based data consistency step, you can clearly see some artifacts here. This is hallucination. Okay, so this can occur. So sometime when you have less amount of data, in this case we particularly use less amount of data. These architectures are well suited when you have less data. They train very well. So if you use a model based deep learning architecture or a model, this particular architecture which has a conjugate gradient based data consistency, then you get very good results. Okay, so this is another example where you see grading reconstruction versus model output. So you can say this is a experiment done at 6-fold acceleration. So this was your ground truth image. Then you took only 1/6 of the samples. Then you applied your A operator on those samples, and you got something called regrading reconstruction, which is basically A transpose Y. From there, you did your model architecture with,
Sir,
in this case,
excuse me, sir.
yes,
Sir,
yes,
actually, I think there is a query from uh, one participant how
yeah,
to
please tell.
decide the number of unrolling networks.
Yeah, so yes, definitely. So how many unrolls you have to do? So definitely, as you see from this image, more the number of unrolls, better it is. Okay, but it really depends on how much GPU memory you have available. Practical scenario, if you consider. Okay, so here suppose you have a 12 GB GPU versus you have a 40 GB GPU. So there you can do more number of unrolls. So one thing we know for sure, higher the number of unrolls, better is the quality. Why? Because the theory says that. Okay, but how do you choose? You take the maximum that you can take in your particular application. That is what you can do. You start with something like 5. So definitely first experiment should always be 1. You do only 1 unroll, then you do 5 unroll. If you can still fit, you can go more, like that. This is only practical experiment we can do about it. Yeah, it also depends on architecture within each unroll. How complex is your architecture? Okay, I hope I'm clear. Yeah, let's move on. Okay, so this was about the MR image reconstruction problem. In this particular problem setting, let's look at the something called a trajectory optimization, how you can further improve your reconstruction results. Okay, so if you just recall this process, I had said so far we have only looked at the reconstruction algorithm. We looked at one particular architecture, model architecture. We looked at the general framework. In that particular framework, you can use any kind of neural network and you get the multiple kind of different architectures. Okay. Now that is not the only way to get a solution. Solution really depends upon how you are acquiring the samples. In this particular case, you have a variable density sampling. So variable density means density is more in the center, less is the outside of the K space. So this area is called K space. This is the Fourier transform of your image. This is called K space. So this is a one particular kind of sampling. But is this the best sampling pattern? Or are there some other kind of sampling pattern then we can fix for our one particular kind of problem statement? For example, like if you have a in your hospital, so many patients are coming for the knee scan. You have a so if you really want to accelerate the knee scans, so you have a fixed data sets of thousands of the patients, and you can learn your trajectory that should run on the scanner such that you get the best quality with the fewer samples. So problem statement is like for a given data set, you want to learn the trajectory that gives you the best result, because you don't know how much should be the undersampling. Should you do 2x undersampling, then time is more. If you do 6x undersampling, then reconstruction quality may not be good. So there is a trade-off. How many samples you have? If you have all the samples, then you have the best reconstruction quality. But time is more in that case. So you want to optimize. So you want to take as fewer samples as possible, which means you want to do more and more undersampling. So in that case, which kind of sampling pattern should we use? There are multiple different kinds of sampling patterns based on the different applications and types of MR. So not all are applicable to all the scenarios. Some are applicable in some scenarios, some are applicable in another scenario. How you move in your K space, that really matters. And how a specific sample has been acquired, that determines your image quality. That has a huge impact on your image quality. Okay, so reconstruction quality really depends on the acquired samples as well as their locations. So it can be a Cartesian or it can be a non-Cartesian location. For example, it is not necessarily like, suppose you have only Cartesian locations. So 1, 2, 3, X and Y. Okay, 1, 2, 3. So it is not like you will take samples only at these locations, because human body is a continuous body. So you can take sample anywhere in between. So decimal numbers are also allowed. If you allow decimal numbers, then you cannot anymore use a Fourier transform. You have to use something called a non-uniform Fourier transform, because that allows non-uniform grids or no irregular data sampling. Okay, so if you utilize a NUFFT or non-uniform fast Fourier transform, that gives you humongous possibilities to improve your trajectory. Okay, so with this background, we have a problem formulation like this. Now again, y is given to you. What you are interested in? You are interested in the k. K is representing your trajectory that you want to optimize. Okay, tau is representing how you are acquiring the data. It is representing your non-uniform fast Fourier transform. And x is what you are interested in. Okay, now we are talking about something called a single shot acquisition, which means when you are acquiring the data in a single shot, in a single TR, you are acquiring the entire data of your slice. Okay, in that case, signal decays significantly. When signal decays, that reflects something called a blur. So whenever you have a less signal, the reconstructed image has a blur. So that makes your forward model more complex. Now you just don't have a undersampling, you also have blur inside it. So this becomes a very complicated problem statement. You see, it has a undersampling, it has a blurring, as well as it has a multiple coil sensitivities, as well as it has noise. So both artifacts are there, noise is there, blur is there. And Y is your blurry measurements. Y is your blurry measurements. So once you have a blurry measurement data, how you can reconstruct back the image X? Again, it is a simple linear inverse problem, but the A operator got changed. Okay. So we can little bit hurry up here. So we can find the initial solution using conjugate gradient. So everything is less like that. And initial solution, which is a zero field reconstruction. So that simply you find using taking the Hermitian or the conjugate transpose in this case. And then you get something called a sense solution. Sense is a very famous algorithm in the MR literature. It stands for sensitivity encoding, which is a solution to the Tikhonov regularization if you look from the mathematics perspective. So you solve a Tikhonov regularization using conjugate gradient and you get a solution. T is representing your NUFFT. So because you are using NUFFT, you don't have a simple inverse. You are solving some kind of iterative problems. Okay. So now this problem becomes much more difficult when you have a blur inside it. What do I mean by that? Suppose you had a ground truth image and you did some 8x acceleration. Okay, so this is how your zero field blurry image is looking like. It has a PSNR of 17. Now, if you just look at the initial reconstruction X naught, which if you do not have any blur, then reconstruction is very good. It has a PSNR of 35. But in the presence of blur, you have a PSNR of only 19. So although they are looking very same, so this is a much more blurry. If you zoom it and see, it is much more blurry image. So in the presence of blur, how do you optimize? Okay, so we had a particular pipeline that this is the work we done here in G Healthcare. But yeah, this is not like guaranteed to come on the scanner. So it is ongoing research. That is just a disclaimer. Okay, so what is going on here? So you have an image. What you do something called a non-uniform Fourier transform. You utilize that and you sample your data. So you will have a undersampled data with you. Then you add a blur on top of it. Okay, so then you get something called a blurry k-space. Then this is a k-space data, so you have to take the adjoint operation to get a zero field reconstruction. This is will be your image. This will be your image domain data. Here it is a k-space data, which is all just points only. Then you utilize sense algorithm. It will remove all the undersampling artifact. Most of the artifact will get reduced. Okay, so artifact will be reduced. Now you utilize your neural network to remove the noise, to remove the blur, and to remove the remaining artifacts. Okay, and you can use a simple neural network. You don't have to go to the model-based deep learning architecture in this particular setting. Because if you're interested in solving the problem, you don't have to go to the most difficult architecture at first. Okay, so this is how you generate your training data. Okay, and during inferencing, your patient will go into the scanner, which has a learned trajectory K. Then you do the inverse Fourier transform, which in this case is adjoint operation. Then you run your sense direct network and you will get the image. The main point here is that the trajectory has to be on the scanner. Okay. So now how do you simulate it? So how do you train the network in this particular network? So because you are changing the trajectory, that trajectory cannot be just randomly you can change. You have to put certain constraints, the physics constraint on the trajectory that we are going to learn in this case. Okay, so our network has a network parameters theta as well as the trajectory parameter k. What you are doing a joint optimization of both of them, trajectory as well as the neural network parameters. Neural network parameter will give you the reconstruction. K is representing your trajectory. So you minimize the loss. Total loss is your task loss and your constraint loss. What is your task? Your task is simply image reconstruction. In image reconstruction, L1 plus SSIM is a good loss. But what is the constraint loss? Constraint loss is saying your velocity and acceleration. This is basically what is your velocity and acceleration of a trajectory. So if you have a trajectory, you have 2 points on the trajectory. So you take dv. So s is the distance. So you take ds by dt. That is your velocity. And then you take dv by dt. That is your acceleration. So you put like they should be minimum. you put this particular constraint on the between the 2 points. You have to put this kind of constraint that allows you to learn a trajectory which is a smooth trajectory. We want to put a smoothness constraint here. Okay, so this is one particular example. Visually, it is much more clear. So you start with some random points, which is the variable density. You cannot test on the scanner. You cannot just simply run these random points. You have to have a connection between the 2 points. So you use something called traveling salesman's problem, and you find which point you should move from where to where. So you get connection between the points. So you get something like this. Okay. Now you can see here there are sharp turns here, very sharp. Everywhere these are very sharp turns. You on a scanner, very sharp turns means high gradient, which means high noise you can get or high eddy currents and all. Okay. So you want a smoothness constraint. So during training, once you finish your training, network will optimize the trajectory with respect to the physics constraint. Then you get a much smoother trajectory here. You can see the zoomed over area. You can see this much curvature is much more smoother than the middle one, center one. So this is what we are getting with respect to the physics constraints. Okay, so you can read more about them in the pilot paper. This particular paper describes these constraints very well. Okay, so this is the evaluation of your trajectory. How does your trajectory looks like? Okay, so if you do 8x acceleration, your image looks really bad. But if you use same 8x, which means number of points are the same, but the trajectory is looking different than the middle one. Middle is a Cartesian trajectory, which is having fully sample center and everything else is uniform. So this is like a uniform sampling. Center is fully sampled. This is a completely random sampling, which is a learned trajectory. This has been optimized for this particular data set. Now you see initial solution, which is a regrading reconstruction. This is not your final image. So if you compare between these two images, you can see this is significantly better. For the same 8x number of points, this gives you much better image than this image. As a starting point, this is a zero field reconstruction, which is a starting point. Now, this is again a different example. So now this is the final output of the network. Okay, you can see all the details. So this is the blur that has been removed from here to here. If you notice these structures are very well preserved. So this is your final output of your neural network. And this is the input that is going inside the architecture after the sense and everything. Okay, so this is like a joint optimization. This is a very interesting problem statement. Yeah. Okay, so if you guys have any doubts so far, just let me know. Okay, so otherwise we'll move to the next topic of the kernel's conversion. So we'll see another application of the model-based deep learning architecture here. Just give me 1 second. Okay, so let's start on the CT kernel conversion.
Dr. Raymond, there is one question in the
Yeah,
chat
please
box
tell
that
me.
instead of undersampling, can we go for oversampling to obtain a super resolution image?
So yeah, if you're saying so, there are multiple things you're saying here. So if you do oversampling, so if you want to do super resolution, definitely you can do super resolution. So how do we do super resolution? If I just draw it here, so this is your case space data. So if you only acquire this much of the K space, okay. So suppose this was your 256 by 256, and you only acquire half of it. Suppose 128 by 128. Then you can do oversampling, which means not really oversampling, but you can utilize some algorithm. Any particular algorithm, iterative algorithm or a neural network. You already had this data. You will learn using neural network and fill this data also. So earlier this was 0. All this data was 0. So you had less data. And now you filled it with specific values by using your deep learning and some other algorithm. So this become your super resolution problem. And definitely there are so many research going on this one. And this is very interesting problem where you try to fill everything. So yes, you can definitely do using deep learning this one. Yes. And these approaches. Yeah. From undersampled data to fully sampled, or you if you are referring to as it as a oversampling in that case. Okay, so let's see the CT kernel conversion. What do we mean by this? What is it? Okay, so yeah, we are from MR now, we are switching to CT. So what I do is I primarily work on solving inverse problems. So whether this is MR or general images or CT doesn't really matter. We always work with some experts, domain experts. So this always, everything we do in collaboration with someone. Okay. So this CT images, when you are acquiring the data, again, when you acquire the data, this is something called a sinogram data in CT. Like in MR, the data is called a case-based data that is coming from the scanner. In CT images, the data that is coming from the scanner is called sinogram data. Once you receive the sinogram data, you apply something called a CT specific kernels. So there are certain kernels that you apply on the data. What do we mean by the kernel? These are nothing but the filters. You have the specific filters. Whenever you have a filter, you can easily take its Fourier transform and just the absolute value of the Fourier transform. That becomes your modulation transfer function. That is what I am showing here. So in CT, you have specific kernels. Specific kernels, you have corresponding to the kernel, you have different modulation transfer functions of those kernels. So what these curves are representing? These curves are representing MTFs. So this is the MTF of the lung kernel. Lung is a specific kernel that is used to see the lung images. So if you have a sinogram data, that can show you anything. Okay, so if you want to get an image which has a very low noise, then you utilize something called a standard kernel, which is the red curve. If you want to see the bone images, then you utilize something called the bone kernel. Detail kernel is another smooth kernel. Okay, so these kernels are the different kinds of filters that you apply on your images to reconstruct the images. So this is a more visual example of what these kind of images look like. An image which is reconstructed with standard kernel looks like this. So it is a very smooth image here. This lung images, because lungs have to look very sharp, you want to look every single detail inside the lung. So that is with a lot of mid frequency boost it has here. So this is a lung kernel image. Again, bone kernel and detail kernel, if you look at the horizontal axis, this standard kernel is dying here, whereas the bone kernel is dying here. So it has a much higher bandwidth, which means it has much more finer details here inside the bone kernel. These details are suppressed here. All the details are available here also, but this is the suppressed details. Okay, so standard and detail, these two are called your smooth kernels, whereas these two are called your sharp kernels. Okay, so you have two kinds of kernels. I mean, these are just 4 examples which we have shown here. So there are several kernels here in GE and many more in some other companies utilize so many kernels. But these are nothing but your filters basically. You filter your sinogram data, the raw data that is coming from the scanner is called sinogram data. You filter your sinogram data using some kind of kernels to see some different kinds of details depending on your application at hand. Okay, so whatever is the downward task, based on your downward task, what is that you want to look at? As a doctor, you will know that okay, this particular kind of detail are best to visualize in this particular kind of kernel. Let me reconstruct my image using this particular kind of kernel. Okay, so if for example for a same data set, if you look at a slice in a standard kernel or a lung kernel, they look very different. Okay, different kinds of details are highlighted. So here you are more interested inside the lung, so then you use a sharp lung kernel. Same is true for like a detail or the bone. So this is a specific image of the inner ear, inside the ear. Okay, so this is particular structure is your inside the ear. So there in the bone kernel, you get much more details. So all these structures are important structures here as well as here. So you want to see the 4 finer details. So the problem statement that we're talking here is this. If you do not have a sinogram data, you only have one particular kind of image. For example, if you have left image, how can you go to the right image? That is the problem statement that we have at hand in the absence of sinogram data. If you already have the sinogram data, then you don't need any algorithm. But sometimes what happens, you only have a image domain data. Because sinogram data is very huge, you don't really save that all the time. So you discard the data to save your storage. Okay, so in that case, if you have only one particular kernel image, How can you convert it into a different kernel image in the image domain? That is the problem statement that we have. If anybody has any doubt in the problem statement, do let me know. Okay, so it is a simple statement. It is an image domain kernel conversion. From left image, you want to go to from a smooth image, you want to go a sharp image. You can also do the other way around. Okay, so from one kernel image to another kernel image in the absence of sinogram data. That is the problem statement that we are talking here. Okay, so simple. So definitely there are several methods. So this is one particular method in 2011. So which is called a direct kernel conversion. Okay. And you can simply use a direct kernel conversion. What do we mean by direct kernel conversion? So we pose it as a simple forward problem, which means you have a standard image, which is a left image, which is a standard kernel image. You apply the operation A on it. What is this operation? We will just see, and that will give you the lung image. Okay. Now, what is this A operator? In this case, A operator is having a Fourier transform. The ratio, what is the ratio R? Ratio is the ratio of the MTFs. And what is the MTF? MTF, I told you, this is the Fourier transform, absolute value of the Fourier transform of the kernel. Okay, whatever is your kernel, take its Fourier transform, take its absolute, that becomes your MTF. So you take and then you rotate it, make it a 2D MTF, and that becomes your ratio image. Once you have your ratio, then you apply the ratio in the Fourier domain. So you have taken the Fourier transform of your image. So in the Fourier domain, you will apply the ratio and then come back to the image domain by taking the inverse Fourier transform. And that will give you this image, lung image. Done. Simple linear filtering will give you this is called a direct kernel conversion. Simple linear filtering you will do. So what happens? It can enhance noise and artifact because every frequency is present here also. If it is a detail image or if it is going from standard to sharp, every small detail will get enhanced. So you will significantly enhance the noise and artifacts. What is your goal? Goal is to control the artifacts and the noise while doing the sharpness of the features. So you want to control your inverse noise in this particular example. Okay, so how do we control the noise? So then we can pose it as a linear inverse problem. Again, you see the kernel synthesis is nothing but a linear inverse problem. You have an input kernel image. Why? You know this. You know A operator. What is your A operator? It is the ratio of the input to the target kernel. Okay, that gives you your A operator. This is in the Fourier domain. Then you have a X which you want to know, and N is you are assuming there is some additive Gaussian noise. In this particular case, N is not a simple Gaussian noise. Later we will see. N is CT specific noise. Okay, but we are still assuming it to be additive just to simplify the problem. Or like no model, no forward model is a good model. It is just the approximations. Okay. So how do we really construct the A operator? Again, this is your A operator. We already saw it. It is the ratio of input to the target kernel 2D MTFs, not really the 1D. It is a 2D MTF. Okay. Yeah, if anybody has any doubt, you can ask. Okay, so let's move on. Otherwise, so forward problem formulation, like a problem formulation is everything. Once you know how do you formulate your problem, then it is simple whether you use iterative algorithm, deep learning, whatever way you want to solve. Okay, so simplest way I was telling you in the very beginning, we can solve the problem using Tikhonov regularization. This is very particularly important if you want to utilize because it is a direct extension of if you want to utilize a deep learning. So if you change the regularizer to something like a deep regularizer x minus z, okay, where z is the output of a network, of a output of a neural network. In that case, how do you solve a Tikhonov? Will give you a direct relation to your neural network. Okay, so let us see how do we really solve it. You simply take the derivative of this equation. So you get the normal equations. Then you can simplify it because we know what is the structure of A. A is your this whole thing from here to here, right? So then you open the bracket, simplify it, it becomes your this operation. Okay, so this is your now your equation. The normal equations are like this. I mean, I know I'm going a little bit faster here, so because these are a lot of things are repetitive, a lot of things are just like a arithmetic or like simple calculus here. So okay, so we are skipping a few details here. Now if you take a Fourier transform on both the sides, you can further simplify this equation. Okay, and then the final solution is just this equation, and this looks like a complicated one, but it is a very simple linear filtering. Okay, this is very much related to your winner filtering that you do in the signal processing. Okay, with some regularization lambda here. So Tikhonov regularization here, the benefit is being an analytical solution. That is the point I want to highlight here. This is a one-time linear filtering that gives you a very good analytical solution. Okay, but it, because it is a single filtering, so it has its own limitations. Okay, so you want a better solution. That is where the deep learning based solutions come. So you can definitely do a supervised learning. You take your input data, you take your correspondingly matching ground truth images, and you train your neural network. Okay, and you minimize some loss function. In this case, suppose MSC is what you are minimizing. Okay, everything you don't know the physics here, right? So from suppose now, because in not all the domains have lot of data available to you. So how can you learn from a single slice? So in CT you typically get like hundreds of slices. Each slice is mostly 512 by 512. Now can you learn? And they are all like one particular anatomy only. If it is a head exam, all the slices are related, consecutive slices. Okay, maybe some 0.3 thickness slices spacing. If it is cardiac exam, all those are continuous slices. So they are very much related slices. So in this case, a lot of redundant information is there. Can you really learn the transform from a one single slice? That is what we are exploring here. Okay, so if you do not have a lot of data available with you, how can you really train the neural network with explicit physics information involved? Okay, so what we can do, we can utilize something called deep image prior. Concept is very simple. So like in a traditional supervised learning, what you do, you have a input data with you have your network prediction, and you minimize the mean square error between actual ground truth and the prediction. Okay, so this is what we typically do. Now in self-supervised learning, how you can do in particular in deep image prior, what you do is in deep image prior is this second thing. This is your deep image prior, this whole thing. So what you have, whatever network output you have, on top of that, you apply your forward model A, which gives you to the measurement domain. It will take you back to the measurement domain, and you calculate the error in the measurement domain. And your neural network, in this particular case, act as a regularizer. Okay, so if you just expand it a little bit, what you will see. We have written AX hat. What is X hat? X hat is a output of your neural network on the data Y. Okay, so f of y goes into the neural network. It is parameterized by theta, and f theta y is a neural network. So that acts as a implicit regularization in this case. Okay, so this is the concept which is very powerful, and deep image prior has shown numerous application. It works really well. Even on the measurement data, you can train your neural network very well. Okay, so as a loss function, you utilize it as a loss function. If you do not have a ground truth, you can utilize the loss function on the measurement domain itself. Okay, but what is the architecture that we can use? In this particular case, we utilize a different kind of model-based deep learning architecture called a Newman architecture. Okay, so Newman architecture was originally proposed in this paper by Greg. He was my lab mate. So this, now you utilize a different regularizer. Now this is not a x minus z. If you remember, if we had utilized this x minus x, this regularizer, now this is a different form of regularizer. So you are not limited to anything. You utilize a different. R is representing your neural network. In this particular case, R is right now representing a matrix, so that you can take a derivative and all using a positive semi-definite form and all. Okay, so you simply take a derivative, set it to 0, you get a normal equation. So you want a solution to this problem. So Newman series is a concept that allows you to take this inverse. So the problem is, how do we take this particular inverse? Okay, so we can utilize Newman series to approximate the inverse. Now once we know how to approximate the inverse, we can definitely get the solution. Okay, so how do we do it? So we know what is a geometric series, right? Everybody knows a geometric series. This is like that. So Newman series is exactly like this. If you have to take the inverse, you go it like this. With the constraint very similar to that, this is called the operator norm. So you have a definition of operator norm here. In as we have some time constraint, so we'll go ahead and but you just see, notice it is very much similar to geometric series. Okay, so what we are interested in, we are interested in the inverse of this whole thing. Once we know how to take the inverse, we have a solution x hat. Okay, so now a, let's see here. Okay, so this is what is a Newman series here. Okay, now if you put I minus a as some this number eta times b, so a definitely becomes I minus eta b, and you put these values here. So I minus eta b you put here, and I minus a inverse which you put here. Then if you substitute these values, you get this. Okay, so b inverse is defined like this. Now you can put b as your this thing b. Okay, so this is the inverse that we are interested in, which we can approximate. So this is an infinite series. Okay, so but we don't really have to go infinite. We can take a fewer steps, maybe 5 steps, 10 steps, just like the unrolled architecture. Okay, this become a different kind of unrolled architecture that naturally occurs from the Newman series interpretation of the, again, your inverse problem, its solution. Okay, so this is the architecture that we have. This is the solution. So I hope you are following up this simple arithmetic operations here, right? So we get a recursive solution to this network regularized problem. So this was our analytical solution. We know now how to take the inverse, right? So in the last slide we saw that we can put this whole thing as a series, and that series is this series, and you have A transpose Y as it is, and eta was there in the front. Now if you expand it, just expand. So assume this whole thing as a x naught, which means this thing plus this thing. This whole thing is your x naught. Then you can do the some simplification, and that simplification will give you a recursive solution. So if you just open this summation, so what we have done, nothing but open the summation. Okay, and we define certain things. So we define a recursive formula which you can verify that it follows exactly like this. So x1 first term, the second term just become like this. This is the second term. Okay, so like x1, suppose you wanted to find x1 here. So this is the x times x naught, which is your first term here. This is nothing but your x1. This whole thing is your second term. Okay, so like that, sorry, x2. So like that, so x hat, which is your solution, is nothing but a sum of individual terms. Okay, so what are these individual terms that we have defined here? So this is the recursive formula that we defined. And if you represent it in the form of an architecture, how does it look like? Xj minus 1 is a input to your neural network. I minus eta times A transpose A. This is a constant operation. It does not involve any training. Okay, R is your neural network. This is your like a DW architecture. This is your like a DC step. This is like your DW step. And then you add back. So this whole thing you can represent in this form. These are equivalent, just a representation thing, nothing else. Okay, so from x naught you can get x1, from x1 you can get x2, exactly same thing you can repeat. So you see this mathematical interpretation of Newman series actually leads to a neural network architecture, and then which gives you a solution x hat. Okay, so this architecture has the skip connections which basically help you incorporate the physics information more effectively. Okay, so and then you learn the weights of the neural network using a single slice and apply it on the whole network architecture. Now the thing is, how do we handle noise? That is the one thing that is pending. So if you see a random Gaussian noise, so this is a random Gaussian. Okay, this left one, this is a random Gaussian. Versus this right side is the actual water phantom data. So this is the actual structure, texture. You see, there's a huge difference between the texture, left side and the right side. So this kind of water phantom data is what we utilize together with the input to the architecture. We utilize water phantom. Then we pass it through the zero field reconstruction, then pass it through the neural unrolled architecture and train the architecture in a self-supervised manner using this loss function, which is just the L1 no. So this is very much like a DIP. Okay, and then once we train the architecture, we apply it on the whole volume. And whole volume, I told you, they have a high correlation among themselves. Okay, so this is the result finally that we get. So you see on the left hand side, this is a standard kernel image. Right hand side is a ground truth image that we had already for a particular subject. And the proposed architecture gives you this. What do we want to highlight here is you are suppressing the noise here. So you are sharper here from as compared to left hand side, you are sharp. As compared to right hand side, you have less noise in the middle one. So that is the benefit of both the worlds. You are able to reduce the noise by using the concept of water phantom noise, and you are able to make it sharp using a Newman architecture. So this is another slice. Again, this is example from standard to the lung conversion, and you can clearly see noise in the soft tissue region is very small here as compared to the left hand side and the right hand side, and this is much more cleaner image. Okay, this is a sagittal slice I am showing right now here. Okay. And this is one particular example that I was showing earlier was a detail to bone conversion. This is a head exam. And you can see from the left to right, we have certainly made the network is able to make it sharper. And you can see fine details are much more visible both here and here. Even if you do not have this, you can utilize this method and go from left to middle. And the ground truth, I mean, we are just showing the ground truth for the comparison purpose. In reality, you can deploy this model and get the detail to bone kernel conversion done using this particular method applied on the whole volume. So you can very much incorporate this. Okay, so this is the overall things that we learned. What we learned today was about the linear inverse problems. In particular, we learned about the model-based deep learning architecture. And we saw a few examples in the MR image reconstruction, trajectory optimization, as well as CT image regression problem. Okay, so yeah, feel free to ask any doubts if you guys have. Yeah, so that is all I had. And thank you very much for listening.
Yes, Dr. Hemant Parik, please unmute yourself and you can ask.
Sir, sir, my voice is audible.
Yeah, yeah, very much.
Yes, you're audible.
Sir, I am also working in this field, and my research topic is like image fusion. And if I want to do research in using the use of sparse representations, like we uh, take the two images and convert into more accurate image. So there are some other alternative method.
Mhm. I'm sorry. So when you're saying image diffusion, which kind of fusion you are talking? Not sorry, diffusion, fusion.
Yeah,
Which
I'm
kind of
talking
image?
about dictionary learning technique.
Okay, and fusion of what?
Image,
Which kind of images?
like medical, any image.
Mhm.
We can take the CT scan image. We can take the any
Yeah,
MRI scan image.
yeah. So yeah, you can definitely do. So if you have an application at hand, like, so if you want to fuse, for example, a low resolution image and a high resolution, so if from the, for example, certain scanners can give you very high resolution images, but they are very small size. So spatial resolution is not very good, but radial or temporal resolution is very good. On the other hand, you have certain kind of images where you have very good spatial resolution. Somehow you can definitely use sparsity and dictionary learning, deep learning methods to get features of one particular image and features of another particular image and get best of both the world. Definitely it is possible. So image fusion has been used so much in different applications like astronomy and all. Also they use, they do the fusion and get the result. So the main thing comes is how you are going to extract the features and how you are going to combine them. So you utilize one of them as a prior, another one as a data consistency, and you can solve the problem in a classical manner, as you are saying, using dictionary learning and all. So you learn the features. Definitely, it is possible. Yes.
Okay, okay, sir. Thank you.
Sure.
So, any any questions from the participant side? Okay. So, okay, okay, Dr. Sophia, please unmute yourself and you may ask. Dr. Sophia, you can unmute yourself and you can go ahead with your query. Okay, Dr. Sophia, you there? Please unmute yourself and you may go ahead with your query.
Or maybe she can type in her query in the
Yes,
chat box.
yes, yes. Please type your query if you have anything. Okay, Dr. Sophia, please type your query over here in the chat box, or otherwise you can unmute yourself and you may ask.
Well, I think she might be having some problem with the system.
Yes,
Okay.
yes, yes. How do I get the informative information? Uh, Dr.
Little bit
Hemant,
subjective. Like, what do you mean by the informative information? Mostly, whenever, yeah, from the
from the
case
case
based.
base. Yes.
Okay, so like when we have a case-based data, definitely you have some interpretations of your case space. For example, the center of the case space usually represents your low frequency information, which here represents your contrast information, like how should it look like. So certain features of your image, like the edges and all, they are mostly present in the high frequency regions, like the towards the periphery of the case space. So center represents your contrast information, periphery represents your fine details. Now both are informative information. How you utilize it, it is up to you. So you have to decide your undersampling such that you preserve enough of your contrast as well as enough of your higher frequencies. Both are informative and both are useful in final reconstruction, depending on what you want to emphasize. Okay.
Yes. Any queries from the participant side? Okay, so there is another query in the chat box. So, Dr.
Okay.
Hemant, if
Yeah,
you
let
can able
me
to
see.
read it out, yes,
Yeah.
please.
Uh, how do we get? No, I think it is a general comment. Thank you.
Okay, okay. It is
I think
general comment.
it's not a query, but a
Ah,
compliment
welcome.
for Dr. Hemant.
Yes,
Sure.
yes. Very,
Thank
very,
you.
very highly insightful session. Okay, okay, madam. Then we supposed to like end the session over here. Okay, so
Yes, yes.
thank
So,
you. Thank you, Dr. Hemant Agrawal. So this session was very insightful. So really, it's began with the basics of MRI and the use of CNN for image construction, which highlighted the limitations also. And the talk also introduces the concept of model-based deep learning, emphasizes the role of MR image reconstruction by incorporating physics constants for more accurate and efficient results. The session also covered a lot of things actually, like from CT kernel conversation, self-supervised learning. So it is a lot more practical insights you offered, which is very helpful in the real world applications also. You have already shown it also too. So these concepts were explained very beautifully, sir. So really,
Thank you
really,
so much.
it is
I'm
really
glad
helped us.
you found it useful. I'm glad, yeah, if
Uh,
somebody help
and
gets some
this
help, it is good. Yeah, thank you.
yes, thank you, sir. Thank you, Dr. Hemant Kumar, for this informative talk. So thank you so much.
Thank you for
So
joining, Dr. Hemant.
thank you.
Thank you,
Right.
everyone.
Okay.
So participants, we are ending our session for today over here, and we'll meet again at 6 p.m. tomorrow. Yes, yes,
Tomorrow,
Dr. Nikunj, you
yes.
want to add
The
anything else?
links,
Yeah.
no, the link and everything is already been shared in the PDF in the schedule.
Yes.
So you can do follow the link and you can join. Thank you for
Yeah. And
the
we
active
will be,
participation.
yes,
Huh.
we will be uploading all resources in the same folder that we have shared earlier in the day. Yes. And regarding the attendance, it will be uploaded on the portal soon. So please don't worry about the attendance part.
Okay.
Okay. Thank you all for joining. Bye bye. Good night.
Thank you. Good night all.